Hello and welcome to this video about the modulo function or modulo operator because it uses two numbers like addition and multiplication. It is represented in computer languages like C and JavaScript as a percentage symbol. It operates between integers and returns the remainder R of A divided by W. All of these numbers are integers, and the remainder R must be a positive integer that's less than W. It can't be equal to W because that would mean that W would divide A, and so R would then be 0. So let's work on our first example. What is this equal to? If we try to find values of n and r so that r is in between 0 and w, then we'll get this expression, and we'll circle the value of r that we want. This value of r would then be the solution to this equation. This is an easier problem because the remainder of any number divided by 10 is always the digit in the ones column. When we write out this expression, we see that the digits can separate out like this when we're using 10 as a divisor. So this is the answer. Now to try solving this problem. We'll write the equation out like this to get the number r, the remainder circled in red. And so this will be the solution to this problem. A last one to try is this one. We can see that the second number divides the first, which causes there to be no remainder, or we could say a remainder equal to 0. So the answer to this problem is 0. Now to look at the addition property of this operator. This looks like a fairly messy expression, which means that the remainder of two numbers added together is equal to the remainder of the sum of their remainders. The modulo function is applied to the right-hand side a second time because the sum of the two remainders can be larger than w. This is good to have a look at because it gives us a sense of how the remainder is preserved under addition. In order to prove this, we only need to prove this statement, that the difference between these two expressions is a multiple of w. We'll let the remainders of a and b be equal to these numbers. Then we can set a and b to be equal to these expressions. When we add a and b together, we'll get this expression. We can manipulate the multiples of w to be together on one side of this equation. We can then factor out the w. So now we have an expression for a plus b in terms of their remainders, and this line proves this theorem. Now we have proved the first equation, we'll have to prove this next one, which is like the first equation, only using multiplication instead of addition. We'll use all of these lines from the last proof that we can use again. We only have to prove this line to prove this theorem. We can multiply a and b together to get this expression. Expanding the brackets gives us this expression. Then we can factor out the w. And after these substitutions, we can get this expression, which proves this theorem correct. So now to define this set called r bar. It is the set of all the integers that have remainder r when divided by w. This set called 0 bar is the set of all the integers that are multiples of w and have 0 remainder. And these are the contents of this set, all of the positive and negative multiples of w. And this is 1 bar, which is the set of all integers that are 1 plus a multiple of w. This is 2 bar, which is the set of all integers that are 2 plus a multiple of w. Hopefully you can see a pattern emerging. So this is what -1 bar looks like, containing all of the integers that are a multiple of w minus 1. And w minus 1 is a member of this set -1 bar. This is what the set w minus 1 bar is. We can manipulate the expression inside the set definition. We can redefine an integer m to be n plus 1, and we can have this new set definition. This is the definition of minus 1 bar, so we've just proven that these two sets are equal. So let us look at all of these sets in modulo 5. Let's look at 0 bar. And these are the contents of this set, the multiples of 5. This is 1 bar in modulo 5. And these are all of its elements, being all of the elements in 0 bar with 1 added to them. This is the set 2 bar, which is all of the elements of 0 bar with 2 added to them. This is the set 3 bar. This is the set 4 bar. And this is the set minus 1 bar, which looks like it is equal to the set 4 bar. This is an expression that we've already proven. If we substitute 5 in for w, we get that 4 bar is equal to minus 1 bar. I hope that you can see why this is true. So now to have a more formal proof of this statement. We get an arbitrary element from this set called x. And this is the general expression for x. We can start to manipulate this expression. We can factorize the w outside of the brackets. We can let this new integer m be equal to this. We can then let x be equal to this expression. And this expression means that x is an element of minus 1 bar. And because all of the lines in this proof are reversible, we can thus prove that these two sets are equal. So now to prove this more general theorem, that the addition of these two sets is equal to this set. We'll start by getting two elements from each of these sets. We can then express these two numbers more generally like this. We can then add these two numbers together. We can then move the multiples of w next to each other. Then we can factorize w outside of the brackets. We can infer from the form of this expression, being the integer multiple of w plus a plus b, that it is a member of the set a plus b bar. And we can see from the form of these two numbers that they are in the set a plus b bar. So we've just proven this theorem. Now to prove this theorem, which is the equivalent statement about multiplication. We can use the information about x and y from the last proof and multiply x and y together to give us this expression. So this is what xy is equal to after we expand the brackets. We can factorize w outside of this expression. And because we have an expression in this form, the integer ab added to a multiple of w, we can say that it's in the set ab bar. So now we've proven this second theorem. Now to show that the remainder of any number exists and is unique, which is fairly obvious. This is how to best express what r is. It is the remainder after a is divided by w, and is in between 0 and w. This number r exists, and there is only one value of r. Suppose there was a second remainder, such that s is in between 0 and w, and this remainder was different to r. Then a would be equal to this equation. So then one possibility would be that r and s would differ by an integer multiple of w. If n was 1, then s would be greater than w, which would contradict that s was less than w. And this would be true when n was greater than 1. If n was minus 1, then s would be less than 0, which would contradict s being greater than or equal to 0. And s would be less than 0 for n being equal to every integer that's less than minus 1. And supposing that r and s exist, then they would satisfy these two equations. We could then subtract one of these equations from the other, which would give us r being equal to s, contradicting r being not equal to s. So we've proven that r is unique. So now we have to prove that r exists, supposing that r didn't exist. Then this expression doesn't exist either. Then a doesn't exist in particular, because it is one of these expressions for a particular value of n, which contradicts the assumption that a exists. So r exists and is unique. Let's look at all the different ways we can write out the modulus function. The first is in computer notation, the next is in bar or set notation. And here we can write out the same thing in congruence notation, in which these different sets are called classes. So now to use this notation to solve for r. We can express this equation differently here, and we can circle what r is equal to. We can then substitute this value of r back into the equation, the answer being 2. Now to find r for this equation. We'll rewrite this equation out like this in standard integer notation. Then we can insert the answer back into the first equation, circled in red. Now to find the answer to this question. We can rewrite the equation out like this, circling r in red. And then we can reinsert this value of r back into the equation that we started with. And here's the last example. We have to find r. It is the easiest because numbers mod 10 are very easy to find. We can express this equation like this to find r circled in red, and then insert this answer back into the equation written in congruence notation and circled in red. So I hope that you have enjoyed watching this video and felt like you have learnt something from it. Please click like and subscribe if you did. Please leave all of your thoughts and opinions in the comments. Feel free to share these videos, and thanks for watching.